Hello, welcome to the Leukopak Lady. This is the 8th episode of Season 3. Today, I close out a set of episodes focused on predictive biology and pre-collection intelligence by discussing why identifying donors with the most robust response to cryopreservation is a key factor in stratifying the donor pool and reducing manufacturing variability. So we think of cryopreservation as a practical approach to solving complicated logistics in cell and gene therapy. Cryo has certainly played a major role in the field, and a positive one. It's essential for scaling allotherapies. It enables centralized manufacturing to succeed on a global scale. It facilitates consistent treatment scheduling, and it increases overall patient access to therapy. But cryopreservation is also a stress test. The process is one of the most powerful stressors cells experience before they ever enter a bioreactor or patient. And the way cells respond to that stress shines a light on variability that already exists in donor biology. Two leukopaks that appear identical before freezing can behave very differently after thaw. One may recover with high viability and strong functional performance, while the other may show poor recovery, reduced expansion, and impaired function. And this variability directly affects manufacturing success, clinical outcomes, and scalability. So think about the stressors that cells are exposed to during cryopreservation. Physical stress from ice crystal formation, which can damage cell membranes. Osmotic stress from rapid water movement in and out of the cell. Oxidative stress, which damages cellular components and mitochondria. And metabolic stress, which affects the cell's ability to recover and function after thaw. Cells must survive all of these stressors and still function in manufacturing and treatment. And not all cells are equipped to do this, but why? Why do some donor cells survive cryopreservation better than others? It comes down to intrinsic biological differences between donors, such as immune cell composition. Some donors just have higher proportion of more resilient cell populations, such as naive or early memory T cells, while others have more differentiated or exhaustive cell types, which are less resilient. Cellular metabolic health. Cells with healthier mitochondrial function recover better after thaw, while metabolically stressed cells are more vulnerable to damage. Membrane composition. Cells from different donors tolerate the stress of freezing differently due to their intrinsic membrane integrity. And activation and stress history. Cells that have experienced prior biological stress may be more susceptible to cryopreservation injury. And one thing that comes to mind here is chronic inflammatory environments that expose cells to constant cytokine-induced stress. These differences represent normal biological variability. They don't reflect donor health in a clinical sense, but they do affect suitability for therapy manufacturing. And so this is why donor stratification is one of the most effective tools to address cryopreservation variability, because it allows developers and collectors to proactively align donor biology with manufacturing and logistical requirements. This involves identifying donors whose cells consistently tolerate cryopreservation well, and prioritizing those donors for key programs that rely on frozen starting material. So stratifying donors based on cryoresilience is part of a broader donor and CSM strategy built on biological data and predictive testing. Assessing markers of functional fitness and stress resilience through pre-collection testing helps with initial donor identification. Using biological performance data from manufacturing runs helps refine donor selection and improve future predictability. And longitudinal donor management allows centers to track donor performance over time, prioritize donors with consistent cryopreservation resilience, and optimize collection timing of those recall donors. In addition to donor selection, process and manufacturing design also play a role. Optimizing cryopreservation protocols, including freeze rates and cryoprotectant exposure, can minimize overall cell stress. Designing manufacturing processes that anticipate differences in cryoresilience from donor to donor improves robustness and reduces downstream variability. Together, these approaches form a comprehensive donor and CSM strategy that helps transform donor biology from an unpredictable risk into a manageable and controllable manufacturing input. And a comprehensive donor and CSM strategy is ultimately a quality strategy. With the goal of predicting cryopreservation and functional performance before collection, biological variability in donors can be managed intentionally rather than just discovered after manufacturing failures. So join me for the next 4 episodes where I discuss how donor stratification leads to the formation of master donor banks. I'll talk about how these banks are built and how they support scalable and predictable allogeneic cell therapy manufacturing. See you then.